We will now see how to realize a common source amplifier using current mirror biasing. Earlier we have used drain feedback around a transistor to set the transistor's drain current to be equal to some given current I0 and use that transistor as a common source amplifier. Now with the current mirror biasing, we can have feedback around just one transistor but replicate its bias around many other transistors and realize common source amplifiers with all of them. Okay. Of course, the condition is that all these transistors must be matched and must be on the same IC, same die, so that they are all at the same temperature and so on. Okay. So we will realize the common source amplifier using current mirror bias. Now what is the current mirror bias? This upper line is assumed to be the supply voltage VDD. I have not shown it always or explicitly pointed to it when I felt it was not necessary, but now I will show that. Here we have drain feedback around this transistor M0, okay, and this gets biased with a VGS, which is the threshold voltage plus square root 2I0 by mu1 Cox W by L, and as I pointed out earlier, this itself, VGS being this, gives you correction for any deviations in VT or current factor and so on. Okay. Now I don't want to realize the common source amplifier using M0. We've already seen that. Okay, we can have a resistor between drain and source and we can AC couple to the input and output and so on. So that's not what I want to do. I have another transistor M1 and M1 and M2 are matched. I want M1 to have the same operating point current I0 and I want to realize a common source amplifier using M1. Okay. How do we do this? Now I can just explain to you the circuit, but it's useful to recall how we did it for the constant voltage biasing. So what did we do then? We had our supply voltage VDD, which of course means that there is a voltage source of value VDD between that line and ground, and we had our transistor M1. What we did was, we knew what VGS we wanted, okay, and we used the voltage divider to get that. Okay, VGS required in that case, I'll call it old to recall that this is the old constant voltage biasing technique, is R2 by R1 plus R2 times VDD, and we choose R1 and R2 accordingly. Okay, and we had our signal source Vs Rs. Okay, now we know that between this terminal and ground, this voltage divider is equivalent to a resistor R1 parallel R2 in series with the Thevenin source, which is VDD times R2 by R1 plus R2. So how did we have this value of bias and this value of signal? We connected this value of bias through a resistor. Now we didn't use an explicit resistor because this resistor is already in place. Okay, so the bias voltage is connected to the gate through a resistor and the signal voltage is connected to the gate through a capacitor. Okay, now we can do exactly the same thing here. The bias voltage is available from here. The VGS required is this one. Okay, it's not this some fixed voltage, but it's dependent on the transistor characteristics and the current that we want to have. Okay, and we have our signal source. Because of lack of space, I'll show it up here. So I have Vs Rs. Okay, what I want to do is to add this bias to that signal. So what should I do? I connect the bias through a resistor, I call it Rg, and I connect the signal through a capacitor C1. As before, we assume that the signal frequency has some minimum value which is not 0. Okay, so if it is 0, you couldn't do that because then the capacitor will block DC. But for a lot of applications, this is good enough. We can assume that the signal has a certain minimum frequency. In that case, we can choose C1 to be finite but large enough. Okay, so now I did this also to show you the similarities between different biasing techniques. Okay, in principle, you have some way of getting a voltage here. You add that voltage to the signal. In this case, you have some other way of obtaining the DC bias voltage and you add that to the signal. Okay, now this establishes VGS, this establishes VGS here. We also have to make sure that VDS is more than VGS minus VT for M1 to be in saturation. So how did we do that with the common source amplifier? We connected a drain bias resistor RD, okay, and the current through this was ID0, whatever the operating point drain current of M1 is. So the voltage across M1 is VDD minus ID0 times RD. Okay, we have to make sure that this is more than VGS minus VT. Now we can use exactly the same technique here. We can bias it through a drain resistor RD. By the way, this VDD of course also means that there is a voltage source of VDD between there and ground. Now if this is in saturation, the bias current flowing through this will be equal to I0. Okay, this is ignoring lambda, this slight dependence of the drain current on the drain source voltage. So the drain source voltage would be VDD minus I0 RD, and our assumption that the transistor M1 is in saturation will be correct if this is more than VGS minus VT, which we can calculate and ensure. Okay, so this completes the bias. The transistor is now biased with a voltage that is derived from constant current biasing. So the difference between this one and this one is that VGS here is a constant. So if VT changes, if VT increases, the transconductance here of M1 will drop, whereas here these two are matched. So if the threshold voltage increases, this voltage itself will increase to compensate for that. Okay, so there is no change to the GM of this transistor. That's why we chose this kind of biasing in the first place. It is better, it keeps the gain more constant. Now we have to connect the load, and that's very easy. We AC couple the load to the drain of the transistor. More precisely, the load is connected between drain and source, but of course this is just a representation of the following stage. It may not be a physical resistor, so we show one terminal as being grounded. Through this capacitor C2 we couple the load, we AC couple the load, and as before we can calculate the value of C2. Okay, so this is what we did with the common source amplifier, and that's what we do now. Okay, and of course the original common source amplifier, the gate bias was derived using a voltage divider. I had shown some representation of that. Okay, now you can see the similarities between these two. The only difference is that this voltage is not constant with respect to transistor parameters. Okay, if the threshold voltage increases or the current factor drops, this bias voltage itself increases to compensate for it to some extent. Okay, so this circuit is the common source amplifier using current mirror bias. Okay, this RG, it plays a somewhat similar role as before. Essentially this RG, putting it here, make sure that the DC voltage here and there are the same. Okay, but the C1 is expected to be very large, so this point will get shorted to that, right, for signal frequencies, and you have to choose RG very large so that there is no division of voltage between Vs and the gate. Okay, so I hope this part is clear. Now what you can do is, for instance, you have another transistor, you want to build a bunch of amplifiers. Let's say you had M2 and you wanted the same operating point and so on. You could use the same bias voltage to bias this through a resistor RG. Of course, I'll call it RG2. The assumption here is that RG, RG2 are all very large. okay, then there will be no interaction between this amplifier and that one. We won't analyze that in detail, but if RG is very large, it's like having separate amplifiers, although they are connected to the same node. Okay, and whatever signal we want to connect to M2, we connect it through another one, okay, another coupling capacitor, and we can realize yet another common source amplifier using M2. Okay, so that's another common source amplifier, and you can bias a whole bunch of common source amplifiers with this constant current derived biasing using a current mirror. Okay, so that's the advantage of this. I hope the logic of deriving the circuit is very clear. Okay, otherwise please go through it step by step and make sure that you understand every one of them. Okay.